sounded very official. I'm sorry. Okay. So a physiologist's perspective on glucagon. Let's get started and have a look at it. So you already heard about Kimball and Merlin, of course, and I also only could find a picture of Merlin, and I couldn't find Kimball. That's true. But the fact is that although they discovered this in 1923, and they gave the name glucagon to the substance, it was really not something people took serious. It was considered a contamination of insulin, and the nature of it was not really disclosed, and it was completely dependent on the method you were using. So people couldn't get a hand on it at all. And in addition, to make things even worse, there were also similar substances to be extracted from the stomach of various tissues by Sutherland, who actually was involved with this. So people were very confused about this, and you couldn't think of an established hormone at all until in 1956. Staubs and Behrens, working at Lilly Company. I didn't know that they were from Lilly, but they are from Lilly. Were from Lilly. They finally crystallized glucagon. These are glucagon crystals, and had it sequenced also, of course. So the point of having them crystallized was that here you had a pure substance that could be injected into animals. So for the first time, it was possible to do something with glucagon and find out what it was about to do. So all these years were really wasted before that. And of course, the big things that happened then was this, for instance, in 1968, where Sutherland identified cyclic AMP because he was using glucagon to stimulate and emulate cyclase. This is his own cartoon of his discovery from 1968. And another Nobel Prize winner also used glucagon extensively. That was Martin Rodbell, and he looked at the interaction with the glucagon receptor and discovered the G proteins. I mean, quite something. This was glucagon that was enabling all of this. The real big hero in glucagon research, of course, is Roger Unk, and I think this is a wonderful picture of him. Those of you who have met him will know that this is a beautiful picture. And he actually created a glucagon radioimmunoassay already back in 1959. Actually, it came before the radioimmunoassay for insulin, just a few weeks, and that was because he was collaborating very much with Burson, Solomon Burson, and he was helping a lot. So, I mean, he never hid that fact that it was because of the interaction with the lab in New York that he was able to do this. And that, of course, created the foundation for the studies of the physiology of glucagon, because before that, you couldn't really do anything with it. So that was extremely important, and they were doing a lot of experiments, and as I said, created the foundation for glucagon secretion. And a big change happened around 1975, where the rabbit 30K was introduced, because 30K was a rabbit that produced a particularly suitable antibody against glucagon, useful for radioimmunoassays. And here we have it. That's 30K. It's stuffed on this picture, but that's the one that, provided, because he was selling the antisera to all over the world, and he was making a lot of money. And that's supported the research going on in the Younger lab. So another important thing about Roger, who fortunately died, he was very old at that time here, in 1975 he created, together with Lelio Orci, the bihormonal hypothesis for diabetes. You can't have hyperglycemia without glucagon, they more or less said. And that, of course, is extremely interesting, because here there was a paper in The Lancet in 76 where Barnes, working with Steve Bloom, said, what about pancreatectomy, guys? Isn't that a proof that you can have diabetes without glucagon? And people were fighting about this, and we will return to that because that's a really interesting issue. Now, the big thing about glucagon is this. This is Pierre Lefebvre from Belgium, who's a wonderful person. He's still alive, and he edited in 1983 the two first volumes of the glucagon book here. And with the third, it's about 1,600 pages of information about glucagon, 83 and 96. And there was a review in Nature, and they said, it's unbelievable that so much can be written about so little. So we were very interested in 30K also, of course, and I did as far as to look at what 30K was actually measuring. And so these are experiments I did on the isolated perfused pancreas, where we are looking at the effluent and putting it on a size chromatography column here to see what 30K measured, and it measured glucagon. I mean, it was okay. And our antisera that we were looking at, they also measured glucagon, and there wasn't anything else, so they didn't really separate from each other in that respect. And that is because most of what comes out of the pancreas really is glucagon, but we didn't know at that time. So nevertheless, yeah, okay, 30K was okay. But we now know that the 30K assay has a very strong matrix effect, and it's off by something like 20 picomolar, yeah. So that's an built-in error, and whenever you look at these old data with the 30K assay, remember that there is a big error, and that 2/3 of it is actually noise. Okay, so how do you measure glucagon? How should one do that? And the problem, of course, is that we have pro-glucagon here and glucagon that is cleaved out here. And if you then would like to use an antibody against glucagon, you'll have to find out where should that antibody bind. And if you just take glucagon and inject it into a rabbit, for instance, what it will create is typically antibodies against this region here. That's 99% of them will be against this region. So if you use this and look at the processing pattern of pro-glucagon, you will see that this antibody will react with glucagon 1-61 from the pancreas, with glycensine from the gut, and with oxyntomodulin from the gut. In other words, you can't measure glucagon with such an antibody. So what about this one up here? Can that be used as the N-terminal specific? We call them terminal wrapping, these antibodies here. Karen Deacon thought of that apt name. But that will also catch oxyntomodulin. So here we have another problem, and maybe other substances also. What about this one here, the C-terminal? Well, that's a good idea. So the 30K was a C-terminal antibody, and the ones we've been using throughout the last quite many years is also a C-terminal, it's here, antibody. The problem is that it will also bind glucagon 1-61, but fortunately, there isn't a lot of it. I'll come back to that, but there isn't a lot of it. So the error is small. So it's more or less okay to use a C-terminal antibody, because once it's cleaved here, you get glucagon and not a lot of other substances. So that's a good idea. But on the other hand, the real method to use these days is, of course, to create a sandwich ELISA with one antibody here and another antibody here. So the art is to get antibodies that are really terminal wrapping, that really require the free, unmodified termini of the C-terminus and the N-terminus to do this. So the question is, do you have that? It took us 20 years to look at this, and finally Mercodia made it and came up with a sandwich ELISA, which is interesting. And that is one of the key discoveries, really, that development of the sandwich ELISAs, because it was necessary to be able to measure the glucagon secretion from rodents. The problem here is, of course, that the sample size is small, so you'll need a method that doesn't require too large plasma samples. And you'll also need a very high sensitivity and a high specificity, all of this. So finally, with the Mercodia assay, it was possible for the first time to measure reliably glucagon secretion in mice and rats. And I must say, I think this is important. Anything that is published before that date in rodents on secretion is invalid. Simply. Because it was not possible. And one proof of this is, if you look at, so these are experiments where we infuse glucose or arginine or mannitol to mice in this case. Have a look at the glucagon secretion in mice. So it starts at 1 minute after the injection, peaks at 2 minutes, and is gone after 6 minutes. That's what it looks like in a mouse. That's really a dramatic dynamic for a secretion of a hormone. So unless you know this and realize this in your experiments, you're completely off. The same for suppression of glucagon, which is as important, of course. Glucagon is supposed to do two things, either being stimulated by amino acids or being inhibited by glucose. See, again, 1 minute, it's down. So you really have to be quick, and you have to have this antibody or assay, otherwise it won't work. Okay, so here we are comparing some of the new sandwich ELISA with some of the C-terminal radioimmunoassays. And if you look at meal responses in control subjects, then it looks good, as you can see on the top. If you look at somebody with accelerated gastric emptying, there may be small differences, but overall it's quite reasonable. Here is a problem. End-stage renal disease in other patients with renal disease. There's a big difference, as you can see here. This is the Mercodia, this is the C-terminal radioimmunoassay. And that's whether you look at oral or intravenous glucose tolerance tests. So the problem was interference by 1-61, because glucagon 1-61, the one that I talked about in the beginning, it accumulates in people with renal disease. So Nikolai did a sandwich ELISA here for 1-61, and if we measure then
1 to 61, you see the secretion here. And if you put on top of, and if you measure with Mercodia, this is what you get. And if you add these two, you get exactly the concentration that we're measuring. So there's no doubt that this is 1 to 61. So in other words, whenever you're doing an experiment in people with problems with the kidneys, be careful. Okay, how do you elucidate the physiology of glucagon? So mimicry is one with the new crystalline and the synthetic glucagon. Yes, go ahead and inject it into experimental animals or people and see what happens. And the other powerful method, of course, is to get rid of glucagon somehow and see what then happens. And there you can use immunoneutralization or receptor antagonists. You can also use gene deletion. That will only apply for the receptor because if you delete the glucagon gene, you will also delete the intestinal glucagon products, and so that won't work. And then, of course, there's somatostatin with which you can block the secretion of glucagon. So let's have a look at it. Physiology of glucagon. This is the full-day plasma glucagon variations in healthy individuals and in obese individuals here. Study that we once did, you can see the sampling over 20 hours. And what happens? Nothing. That's the message. So why do we have this meeting? Why is such a boring peptide that doesn't do anything? It's really amazing. Yeah, okay, let's stand there. Okay, but of course, all the mimicry experiments suggested that there was something about this and that glucose would inhibit alpha cell secretion, found out in Roger Unger's laboratory, and low glucose would stimulate secretion so that you would have a feedback cycle between the liver and the alpha cells with glucose as the intermediate and glucagon coming to the glucagon receptor in the liver. Of course, this is the established thing. That's what came out of all these mimicry things. Let's see what happens if we take away the glucagon stimulus, okay? So here we have some experiments with a glucagon monoclonal antibody, a very, very high power antibody that Christian Brandt did many years ago. And as you can see, it could completely eliminate the rise in glucose after a large glucagon injection in these rats. But this is the interesting part. Did it do anything to glucose? Yes, in postprandial rats, in fed rats, it would lower glucose concentrations by 1.5 millimolar or so. Not a lot. Just 1.5 millimolar. And then if we took fasted rats, 10-hour fasted rats, no effect at all. Now, the textbooks were full of gluconeogenesis and all that, but if you do this simple experiment, nothing happens. And you fasted for 48 hours. We could do that those days. You can't do that anymore. Please don't. Then also nothing happens. So it is not important for fasting glucose levels in the fasting animal. And this was completely confirmed by the glucagon receptor knockout mice here. As you can see, these are their blood glucoses throughout the day up to the left. This doesn't work very well, but yeah. So you can see that glucose is, yeah, those are fasted animals, and it's lowered by 1.5 millimolar or something like that, but nothing more. Nothing more. It doesn't create hypoglycemia at all. That was quite some finding. So now we know that there is something wrong with that, general circle that we had generated here. Let's return to Roger Unger and the bihormonal hypothesis for diabetes. No hypoglycemia without glucagon. And the contradiction here that you can have a pancreatectomy. So let's see a little bit more about this. So there are two important issues that come out of this. Is there glucagon outside the pancreas? And the other one is it true that the hypoglycemia of type 1 diabetes depends on glucagon? Is that really true? So we'll have to analyze this. So of course we have these cells out there in the gut that can react with some anti-sera antibodies against glucagon. And we have them there, of course, and you know that, all of you. So what we did in 1983 was to look at people with total pancreatectomies and do a very careful chromatographic analysis of their plasma. And so this is what you measure with one of these side-viewing antibodies. That's glycentin, oxytomodulin, very nice here. And then with the C-terminal antibodies, they also picked up a signal, as you can see, one that was interpreted to be 1 to 61 and one that was interpreted to be glucagon. But is it true? Is it true? This was in 83. Then comes the modern technology and mass spec and all that, and we did these experiments again. So these are controls given oral glucose tolerance test and controls with intravenous, and then the pancreatectomized individuals, and again we see this rise in glucagon, and this time it's with one of the Mercodia assays, and a sandwich ELISA and all, and a suppression here with intravenous glucose. So that would strongly suggest that there is glucagon outside the pancreas, of course. Now, people were beginning to fight about this, and is it really true? Is that really true? And is the Mercodia assay as good as it is thought? And is it completely rid of cross reactions with these wrong molecules? So they did a new assay, a new development with two different washing procedures. They call them sequential and simultaneous. And they look good in obese subjects. This is meal responses here. And here you have Roux-en-Y gastric bypass, which was really the thing that could distinguish people from each other. So that's one study. So again, we looked again comparing the sequential versus simultaneous protocol here. This is amino acid infusions. Oh, very, very, very nice, completely identical responses. And this is injections of glucagon into people and then measured, also exactly the same. And you can see the individual data here. They're really, really beautiful, complete overlap. So that was not the problem, but here is the problem. So this is 10 obese Roux-en-Y gastric operated individuals during a 50 gram. And here you have the new procedure, decrease, and here you have the old procedure, increase. So what is true? And I'm afraid we don't really know that. If you assume cross reactions with it's glycensine actually, then you can see that you can construct all sorts of similarities to this curve if you assume cross reactions of 5, 10, and 20%. And there is a cross reaction in the old assay. So I'll leave you with that because I hope that the conference could bring us further on to the answer to the question. Let's see. So the other one, is it true that the hyperglycemia of type 1 diabetes depends on glucagon, which is what Roger Unger would say? So this, you all know, this is a beautiful experiment by Jarek. Here you have the matrix error of 30K because he's suppressing glucagon secretion with somatostatin. And if you do that in type 1 diabetics and stop their insulin infusions, so now they don't have insulin, what happens is, of course, that glucose starts to rise dramatically, as you can see, and so does glucagon here. So is glucagon now responsible for this glucose rise? And that's what everybody would say. And moreover, Lee in his Unger's laboratory in 2012 did studies in glucagon receptor knockout mice and found that elimination of beta cell function with streptozotocin would not cause diabetes in these knockout mice. That would really support this view, of course. And here you have it. So this is streptozotocin in a control mouse. And of course, it develops immediately strong type 1 diabetes, right? But this is the knockout mice with the knockout of the glucagon receptor. No hyperglycemia. He was happy down there in Texas, and said, oh, there's proof of my hypothesis. It is really true. We tried to do this also in mice, and there are a number of experiments here. Here we could knock down glucagon, and we didn't really see a difference here. Here we could use glucagon receptor antagonists. We couldn't really see a difference. Here we tried immunoneutralization again, and we really couldn't see a difference when we gave the animal streptozotocin. That would create, as you can see, a very severe diabetes with very high glucose levels. So another experiment that we did recently is in mice again, where we were using the famous insulin receptor antagonist S961, which is really a good antagonist. And so when you do that, you will produce strong, severe hyperglycemia, as you can see here. And what we then did was to put on top of that a glucagon receptor antagonist, which was a good one. And then we could completely eliminate that glucose rise. That, I think, was very strong support for Unger's hypothesis. But it is in mice. Mice are not humans, so let's have a look at humans instead. So this is a very recent study from Petrus using a glucagon receptor antibody as a glucagon antagonist. And this is a study in type 1 diabetes, 12-week randomized double-blind phase 2 trial. There are a couple of them, actually. And what happens? So it does lower glucose concentrations by 10 milligrams per 100 milliliter. Are you impressed? And there is also a reduction in A1C after the 12 weeks. So Roger Unger was probably partially right, as always. Okay, a little bit more about the receptor antagonists. So people have been working with this for many, many years. I even synthesized some on my desk, a yellow one, I remember. Okay, but they were all partial agonists, these peptide-based ones, and they were really poor. They created a lot of confusion in the field, and there's a lot of studies, and don't ever quote them because they're nothing worth. Then there's a lot of small molecules, but some of them are quite good. And they were being, the industry was really engaged in this because of Roger Runker, of course, and worked on this. And now there's also the receptor antibodies. And now I'll put a resume on what happened to the glucagon receptor antagonists. So they effectively blocked the glycemic responses to glucagon. They did lower fasting insulin levels. They lowered fasting glucose levels. Then they decreased A1C quite a lot, actually. So that was the good side. But then what happened, and here I'm using as a model the Merck compound, because the Merck antagonist was actually the best of them. It was also one of the most advanced ones. So what they found with the Merck compound was there was a delayed recovery of hypoglycemia. There was an increased secretion of glucagon. There were increased levels of LDL cholesterol. There was increased levels of hepatic transaminases, and there were increases in body weight. So they stopped the program. That's what happened. This was the best of them. There are also others. This is the LY something from Lilly. And as you can see, it very nicely lowers fasting glucose concentrations in type 2 diabetics and also to some extent in people. Again, this modest decrease that I've been talking about all the time. Completely the same. Probably glycogenolysis that is inhibited. And here we have some of the more long-term effects of the Lilly compound. And over here you can see some traces over the 24 hours of the day. Nice reduction in fasting. Again, these 2 millimoles per liter. And then the meal rises, and they don't seem to be affected at all. No effect on the meal. That was a problem. No effect on meal, hypoglycemia after the meal. Strange. So more results from the Lilly compound. So these are fasting glucagon levels. As I said, it increases the levels. Yes, up to 300 picomoles per liter. That's huge. And the reason is the hyperplasia of the alpha cells in the pancreas, as you can see here in the knockout mice. It's very, very clear here. All the red cells are glucagon cells. It's absolutely crazy. And here are the hepatic transaminases. And here, again, decreases in A1C, very nice results from this antagonist. But another problem, this is the liver fat fraction in these people over 6 months, increasing and increasing and increasing. So liver fat increases. And here comes the most disturbing thing. So these are studies from Philip's laboratory, I'm sure you will hear more about it, where people were with pancreatectomy here were looked at with the antagonist, trying to see if this measurable glucagon would influence the glucose levels, of course. And as you can see here, looking at it, there's a nice effect there's no effect absolutely on the postprandial rise, as you can see over here, but there's a difference here in the controls, as there should be. But the problem is it goes in the wrong direction. There's actually an increase in glucose after the antagonist has been given. That was even more disturbing, of course. But the reason is here. It interacts with the GLP-1 and the GIP receptor. Once you use these high concentrations of an antagonist, you always have to be very careful with the antagonist because they lose their specificity, their selectivity. So there is a strong interaction in these high concentrations with both the GLP-1 and the GIP receptor, and that explains probably that the response to the meals, the effect of glucagon on the meals, all of a sudden disappeared. No, it didn't. It just was incorrect measurements. So these were all the methods to elucidate the physiology of glucagon. And so what is the conclusion? And that's what we will talk about at this meeting, of course. But my proposal is that we have 3 feedback cycles between the alpha cells and the liver. And one is about the glucose that we talked about. One very important one is the amino acids that stimulate glucagon secretion, which in turn increases hepatic amino acid metabolism. And this seems to be one of the most important mechanisms of glucagon actions. And then there's a further 3rd cycle of the fatty acids here, the lipids, where glucagon powerfully regulates hepatic lipid metabolism. And we think that lipids probably also influence glucagon secretion, and this is going to be a new hot topic, I think. So this is it. Thank you very much for your attention. Do we really?
Yes. There's a question over here. Christine is going to come down with the microphone.
Wonderful talk, Jens.
Thank you.
So how valuable is it to measure glucagon concentration in the general circulation relative to the portal blood?
So the portal circulation will always have a higher concentration, and it's about threefold higher, something like that. And that is evident because the portal blood is diluted, if you will, in systemic circulation by about a factor of 3. Is there a take-up of glucagon in the liver? I say no. Others may say yes. And the answer is a little bit uncertain because this is something we can discuss. But you must you must think that there is about a 3-fold increase in portal compared to periphery.
More questions? I have one there.
If you allow an in vitro physiologist to ask a question, because this was, of course, beautiful in vivo physiology, but I'm not so surprised, working on isolated islets, I'm not so surprised that you don't get much effect of a glucagon receptor antagonist when you apply it, because I mean there is actually very little glucagon secretion in excess in diabetic islets. We haven't studied that many, but glucagon, in my impression, is that glucagon secretion is actually already quite suppressed. It's a small subset of islet preps where you actually have a stimulation or elevated glucagon secretion. So from our in vitro experiments, for what they are worth, it's not so surprising. And then the second comment, if I may, is that you talked about the effects of hyperglycemia, but isn't really what you should be looking at, the effects of hyperglycemia.
Yeah, it's a strong stimulus for glucose. No, so I somehow appreciate that also. But I think that the most important here is to realize that, okay, we do have glucagon acting as a kind of fine-tuning, and I do believe that this regulation of the fasting glucose in type 2 diabetes is due to glucagon. I think it's appropriate, it's correct. It's responsible for this, but there is a limit to it. It's not everything. So I think that's the most important.
Do we have any more questions? Otherwise, I can ask. So this is the 100-year anniversary of glucagon. Okay. What's in store for the next 100 years?
People like you working to find out about this lipid feedback cycle so that we can see how important that is. That's for you to work on. So better go back to the laboratory.
Do we have any more questions? Otherwise, I can ask a second one.
Okay.
So antagonizing, agonizing the glucagon receptor in the clinic?
Yeah, so obviously the interesting thing here is this effect on the fat in the liver. We have been through all these debates on using glucagon for appetite regulation, and it works to some extent, but we have all these side effects that we have to look at if you use it. But the problem is the effect on liver fat sufficiently strong that we can treat NASH/NAFL with it. And that is an opening here for glucagon. Perhaps if you can keep the other effects, titrate them well with GLP-1 or whatever you have, then we can have this effect on the liver fat isolated and use it for NAFL. That I think is the big promise.
Mm-hmm. We have a question over here.
So what is the status on the effect on lipolysis and adipose tissue, and is growth hormone involved in that? I wonder.
There was a paper last week again confirming that there isn't any expression of the glucagon receptor in people in the white adipose tissue, and there is no effect on lipolysis. It is, when it happens, it's because you overdose glucagon and you activate the sympathetic nervous system, and that will, of course, cause lipolysis. You know, the tradition has been, ever since Staubstin and Behrens, is to inject 1 milligram of glucagon into people and see what happens. That causes tremendous concentrations of glucagon. It's highly unphysiological and causes a lot of nausea also. So you have to be careful here. But in people, no, it is not regulating white adipose tissue lipolysis. But you know, this is a special thing probably in birds. It is vital. They can't live without glucagon. If they don't have the glucagon effect on lipolysis, they'll fall down.
So what about growth hormone? Do you think that could be activated and thereby increase lipolysis?
So here I will again have to look at what is physiological and what is not. So pharmacologically, yes, that's possible. And that could cause a lot of effects. Also at high concentrations, whatever small amounts of brown adipose tissue you may have, it can also activate that and cause things to happen. There's a big idea out there that glucagon increases energy expenditure in people. Yes, you can force it to happen if you use high doses. Again, the sympathetic nervous system probably. But in physiology, no.
We have a question over here.
Yeah, right here. That was a fantastic presentation.
Thank you.
A quick question on the glucagon receptor knockout or antagonism. Does this, by chance, either amplify or influence the activity of other G-alpha-S coupled receptors within the liver? Can it essentially amplify the
That's a good question. I cannot answer that. That's a very good question. And we don't know everything about glucagon's actions on the hepatocyte. And we don't know all the pathways that are actually activated. As you know, there's a calcium pathway also. And some people suggest that there are even more signaling pathways in the liver cells that we don't know and haven't appreciated so far. So it's a good question. And you can easily imagine that something will happen. Yes, you're right.
And that was all the time we had. Thank you so much.
Thank you. Thank you.
Thank you.